Interferometers are widely used in science and industry for the measurement of small displacements. In most interferometers, light from a single source is split into two beams that travel in different optical paths, which are then combined again to produce interference patterns. Interferometers are used to measure lengths and the shape of optical components with nanometer precision. They are the highest precision length measuring instruments existing.
Today we are going to build an interferometer using LIGO, a laser, 2 mirrors, and a glass slide. I have made a LIGO base plate to mount the laser, mirrors, and the beam splitter. I will mount the laser attachment that will hold the laser. Now, I will place the laser in position. These are the structures that will hold the mirror in place. Then, after choosing the positions for the mirrors, I put a rotatable LIGO piece that in the path of the laser beam and is equidistant from both the mirrors. After placing the mirrors in position, my interferometer looks like this. These guys will hold the glass slide in position. Finally, I will place the glass slide on the rotatable LIGO piece so that the beam splitter can be rotated. Now if I turn on the laser, I should get 2 points of light here. And, by moving the mirrors a little bit, both points can be imposed upon each other. Here you can clearly see the two laser beams that will make the interference pattern. And also the paths taken by the beam from its starting point to the beam splitter, to the mirrors, and the reflected path. If you look closely, you can see some vertical lines on the image that is formed. This pattern is the interference pattern formed by the interference between the two beams. To see the interference pattern properly, I'll be using this concave lens salvaged from an old laser pointer, which I have mounted on a LIGO brick. When the laser beam travels through the beam splitter, it gets split into two beams that are perpendicular to each other and travel towards the mirrors. On getting reflected from the mirrors, the beams retrace the path from where they came from and get merged at the beam splitter while being reflected towards the lens. Both beams get magnified while passing through the lens and form an interference pattern that can be clearly seen. This interferometer requires very high calibration. Even the slightest movement can cause changes in the interference pattern. That's it for today. Subscribe and turn on notifications to get notified about future uploads. Any questions? Ask me down in the comments and I'll try to answer as many as I can. See you again in another video.